The title of my talk today is Towards Precision Medicine with Machine Learning and Computer Vision. First of all, my industry disclosures. I'm a former employee of Google and own Alphabet stock, and a current employee of Tempus Labs and own Tempus stock. So Google probably does not need an introduction, but I'd like to talk a bit about Tempus. Tempus is a data-driven precision medicine company whose goal is to make precision medicine a reality. It was founded in 2015, and right now in 2020 we have about 1,200 employees across 3 locations: Chicago, where the headquarters is, San Francisco, and New York City, and we're also expanding and currently hiring. So I keep using the term precision medicine, and I'd like to first of all introduce what I mean by that. Wikipedia defines precision medicine as a customization of medical decisions and treatments tailored to the individual patient, which then results in the selection of appropriate and optimal therapies. And this involves molecular diagnostics, imaging, and analytics. So in other words, it's a data and machine learning problem. Well, at least for the context of this talk. In reality, there are many other problems that need to be solved in order to bring a machine learning problem into healthcare reality and reach the patient, but we can talk about that some other time. So one of the challenges that precision medicine is trying to solve is that medical diagnostics are not as accurate as we'd like them to be. Here are some statistics from a 2015 JAMA paper about breast cancer diagnosis, and the short version here is that 1 out of 12 breast cancer biopsies is misdiagnosed, which is a very scary number if you think about it. And 1 out of 12 for breast cancer is pretty bad, but it's similarly bad for other cancer types. Prostate cancer, for instance, has a 60% concordance rate only between different pathologists. And this really illustrates what we hope machine learning can bring to precision medicine, to make it more accurate with the help of machine learning models. So if we compare the value proposition of that to other machine learning areas and applications, we have an interesting pattern here. So robotics, for instance, the value proposition of it is mostly scaling and automation. So pretty much doing things that humans can do already, just at a faster and more automated way. Self-driving cars as another application is pretty much a lifestyle optimization. Medical diagnostics, however, are trying to improve the accuracy. And that's fundamentally different because it means we are facing different challenges in how we build these models. So if we're looking at the challenges in these applications, in robotics, it's mostly it's a combination of perception of a scene and taking the appropriate action. And there's a lot of challenges, often in the mechanics and physics about it, but the labels are usually pretty easy to generate. Similarly, in self-driving cars, there are additional challenges like extraordinarily high reliability requirements and real-time requirements, but labels are not so difficult. In medical diagnostics, the labels are very messy. They're very messy and they're subjective. And this poses tremendous challenges to how we need to think about building these models. So if we go back to other applications like robotics or, let's say, self-driving cars, scene recognition, the labels here are usually fairly easy to generate. So pretty much every layman can label different items in a street scene, like electricity posts, buildings, pedestrians, cars, etc., etc. So pretty much what we need to label your data set and train a machine learning model. But if we go back to the medical applications, then we're facing the challenge that we're trying to solve more accurate predictions for something where the labels themselves are very messy and subjective. So one concrete example for that here is in prostate cancer Gleason grading, which is usually graded on a 5-point scale. And this 5-point scale reflects the morphological pattern that a human sees in that microscopy image of a biopsy. And if you ask different pathologists, then they usually disagree on the exact grade of this morphology. For prostate cancer, it's pretty much the 60% concordance rate. So pretty much you ask 3 pathologists and they give you a different answer. And keep in mind that these are experts. These are people who have went to medical school and residency for 10 years and more. So if they disagree on how they diagnose a case, then this really shows how difficult it is to generate the labels. So what do we do with the labels? If we have label ambiguity here, we have different options how we can deal with it. First of all, we can be taking a consensus approach and basically just take the mode of all the different grades by asking multiple people and determine, let's say, if 2 people say it's a 3, One person says it's a 4, we just take the mode, which is the 3. You can also take the average and call it a 3.33. We can also use the vector input and say 343. Or as a final option, we could for someone who's really an expert in prostate cancer and is pretty much one of the people writing the books about this, and can ask them for this grade. So this is the adjudication case where they might look at individual grades from regular pathologists and determine the expert label for this. And they might tell you that this particular case might be a cribriform subpattern of a Gleason 4 that is often confused with a grade 3 Gleason pattern, something along those lines. But this just illustrates that when you're trying to train machine learning models on medical data, you always need to question where the ground truth is coming from. And that's something that is often neglected when you look at public challenges data, where you basically just download a data set and it comes with a certain grade or a certain label. And often we don't really question where the label is coming from. But generally, if it's coming only from one doctor, then you can assume there's a lot of noise in it. And that is one of the key challenges when it comes to building machine learning models in healthcare, that we simply can't rely on the data being clean. And a lot of the work that goes into this is actually in the process of cleaning up the data, understanding the labels, and having the right ground truth strategy. That actually has a much, much more profound impact on the eventual model performance than deciding what exact machine learning architecture to use. So with this context in mind, I would like to talk about a few applications where we're using machine learning to build models that hopefully can advance precision medicine. The first of these is in detecting metastasis. So the specific application here is that we're trying to diagnose cancer more accurately. And to give a bit more context on what the input data here is, so the input images, the way cancer is usually diagnosed is that the tissue sample is extracted via small surgery or via needle core biopsy. And the tissue that's extracted is then prepared with certain chemicals on a glass slide. That glass slide is then investigated by the pathologist under a microscope. And based on the visual inspection of this tissue, they will render the diagnosis. So is this actually cancer? If it is, what grade is it? And that is one of the key steps to determine the treatment. One of the challenges here is because the images that we're talking about need to capture the cellular detail, we arrive at a lot of information. So typically each of these images, when they're digitized at cellular detail, result in gigapixel images. One of these biopsy images is usually equivalent to about 1,000 DSLR photos. So that's a vast amount of information in these images. And that's a challenge because typically pathologists need to review all the content in these images. So in this first application that I'd like to talk about here, the goal is to detect metastasis in lymph nodes that are coming from a primary breast cancer. And one of the core challenges here, first of all, is that it's literally a needle in a haystack problem. So this particular image here is from a biopsy, from a lymph node biopsy, and the image is extremely large in terms of pixels, but then the only metastasis in this image is tiny. So we're talking about 1,000 times 300 pixels in a 150,000 times 100,000 pixel image overall. And if the pathologist misses that area, they would misdiagnose this case with the wrong stage and call this particular lymph node, let's say, negative without metastasis, even though it has metastasis. So this is one of the challenges that they're facing. Another challenge is that there's a very high interclass similarity between benign tissue and cancer. So shown on the left side here is an area of this tissue which is benign, and on the right side we see a cancerous region. And to the layman, these look very, very similar. And even pathologists, as we saw in the statistics in the introduction, often have challenges determining what is really the cancer here. To address this problem, we trained a machine learning classifier where we collected ground truth data, so we know where in these images is a cancer based on what pathologists have been annotating. And because the images are so large, we need to break it down to small tiles. And then for each of these tiles, we know, is there cancer in this tile or not? We can train a machine learning model like Reception, Inception, or ResNet, or anything else that classifies these tiles with a likelihood to have cancer or not. And then at inference time, when we use this algorithm, we can make a prediction for each of these tiles and then stitch it together to arrive at a heat map, which tells us with what likelihood is cancer in each of these regions. So pretty much a standard procedure. And if we do this, we arrive at a model performance that actually looks pretty good. So in this anecdotal example, which I mentioned a minute ago, we see that the machine learning model predicts very low likelihood of cancer in the benign area on the left, very much below the cancer threshold in this model, but is very, very certain of cancer in the right area. So it's performing really well in this particular case. And then if we look at the quantitative statistics over a large data set, we see that this particular model here that we developed a few years ago has a tumor localization performance of 0.91, which is much higher than what a single pathologist is achieving if they're given infinite time in this test. And the nice part about this particular application here is that the model also generalizes to data from other clinics and other scanners. And if you're interested in the details, then please check out the publication here in Archives of Pathology Laboratory Medicine from 2019. Now, building machine learning models is great, but what we really want to do is to take this to impact and assess what other steps need to be done to get it there. And one of the core requirements is to bring these machine learning models into the clinics and deploy them. And one of the ways we would like to do that is to integrate them into a digital pathology viewer. So what we've done here is a test where we integrated this machine learning model into a digital pathology viewer to highlight where's the cancer. And so on the left side here, we see the user interface, or crop of the user interface in the unassisted view. And then on the right column, we see it with the assisted view. And we did a mini clinical trial here where we simulated the workflow and had 6 pathologists times 70 cases review these cases with and without the assistants. And then we measured the accuracy and the efficiency. And it turned out that with the algorithm overlay, the pathologists were more accurate, so they had a 1/3 reduced error rate, but they were also more efficient, in particular for the difficult cases of these micrometastases, where they're looking for the needle in the haystack. They were about 1/3 faster than in the unassisted view. And this is very promising, and it took a few iterations, let's say, of the user interface even to bring it to that point. But there's still additional challenges here to bring it to adoption. And one of the challenges is that digital pathology is not quite adopted everywhere for very different reasons. So what we try to do in the next step is, instead of trying to wait for the adoption of digital pathology, which is still facing a lot of workflow and integration barriers and also quality barriers, we try to turn it around and try to bring machine learning directly to the user, which is a pathologist. And pathologists are using optical microscope in their day-to-day work. So what we did is we took a regular clinical grade microscope, attached a camera to it, and then that camera was taking a video live stream of what the user is seeing through the eyepiece. And then we run a machine learning model, pretty much the one we trained from the digital pathology images, on a compute unit, so a graphics card, and the deep neural network that we trained, and ran inference on that video live stream in order to predict the tumor probability, and then display the output of that, like a heat map or outlines, in a micro display that we projected into the optical pathway, so that the user eventually sees an overlay of the optical view of the tissue with basically head-up display that is updated in real time of where the cancer is or what exactly they're looking at. And this requirement of real-time update is extremely critical, because otherwise it would be pretty useless in the workflow. And we arrived at this system about a year after its conception. Here's an illustration of it. There's also a publication in Nature Medicine from 2019. You can read more about the details. And this was a pretty interesting project to work on, because there were many challenges, including the optics and the integration into the microscope, but then also even just making it fast enough in real time is something we struggled quite a bit with in the beginning. So it started with a frame rate of 2 seconds per frame, but then we brought it down to about 1/10 of that way, it really approached real time. There's also a YouTube video here which you can check out. The link is there on the bottom. If you just search for Google Cancer Microscope, you will get to it, where you can see the microscope in action. So the next topic I'd like to talk about is similar in nature, but it's a bit more complex in terms of the actual data behind it. and that is the prostate cancer Gleason grading, which I used as an additional example. So, quick reminder here, prostate cancer Gleason grading is a classification of a morphological pattern that a pathologist is doing into one of these 5 classes. And as I said in the beginning, there's a very large discordancy among pathologists, which leads to misdiagnosis. So we took a pretty similar approach to the initial machine learning model that I described earlier about metastasis detection, just at a slightly larger scale. So we had more slides, and we collected these from different sources. We scanned them in different whole slide image scanners to get to more variability on the input data, and then had a lot of pathologists actually annotating these data, where we arrived at a total of about 116 million labeled training patches for the model. And what's very important here is that we had multiple pathologists create the ground truth for that, and an additional adjudication step to make sure that the labels are as good as they can be. And then we used a pretty similar approach to what I discussed earlier. We tiled the images into small patches, had a label for each patch, trained in this case an inception network, and then had a second stage that summarized the scores of each small tile into a slight little score. And then at inference time, obviously the same thing. So in the end, you would get a heat map or a multi-class heat map, which tells you the probabilities of certain classes being present in certain locations. And the results of this work were fairly compelling. We were able to train a model that is more accurate than general pathologists. So the accuracy our model achieved was about 69% compared to about 61% of general pathologists. And this is measured when using prostate experts labels as the ground truth. So another way to measure the quality of a label of a model is actually to use survival as a label. So you're moving away from the diagnostic label of a human called interpreted grade to how long did the patient survive or when did they progress. So this is more of a prognostic model where we're trying to stratify patients into high risk and low risk. And when we applied our model and used these labels, we found that the model does a better risk stratification into high risk and low risk patients than general pathologists, but worse than prostate experts. So in this Kaplan-Meier plot here, the optimal stratification would be to have a very large separation between that upper arm and the lower arm, the low risk patients and the high risk patients. And as you can see here, the deep neural network model is in between the general pathologists and the prostate experts. So it's a pretty good result, but there's still room for improvement. Another interesting outcome that we did not really expect, that the model is also able to do more fine-grained classification of the Gleason pattern. So basically, if you look at the subjectivity or the more ambiguous cases where pathologists disagreed, you could make an argument that those are maybe between these discrete classes that are called Gleason 3 and Gleason 4. And when we looked at the model output for those classes, we found that the softmax probabilities were reflecting the subjectivity or the ambiguity that also the prostate experts gave to these. So for instance here, if you look at the 3, 3, 4, the second column there from the left, we see that 2 pathologists call it a 3, 1 pathologist called it a 4, and the model has a similar ambiguity compared to the more clear-cut cases of the patches, which were called, let's say, 4, 4, 4 overall. And this is a very, very promising outcome because it offers the opportunity to make the predictions more precise and more fine-grained, and then hopefully also have that correlate to more specific and more precise outcome prediction. If we look at the morphological patterns here that corresponded to these different non-integer classes, we can also see that the morphologies are really in between these classes of a pure Gleason grade 3 and a pure Gleason grade 4 and pure Gleason grade 5. So there's a lot of room for additional improvements here and further work, but this was a very, very interesting outcome for us, and it's, I think, an additional step towards what we would call precision medicine. And then the last topic I would like to talk about is going beyond diagnosis, and this is addressing a lot of the work we're doing at Tempus. So machine learning at Tempus is actually much more than computer vision. because we have access to multimodal data. So Tempus has a very large sequencing businesses where we sequence cancer patients to determine their the DNA and their RNA profile. We structure clinical data and extract their treatment history and medication and everything. And we also have imaging available like the pathology and the radiology. So we have multimodal data that we can use to do discovery and data-driven research, not only in imaging, but across all of these modalities. And basically, we look at this in two ways, how we can combine these multimodal data sets. First, we can use the data from the different modalities in combination to use it all in one multimodal model, with the expectation that the information from, let's say, pathology images and DNA sequencing and clinical data is complementary and leads to an overall better prognostic or predictive model. The other option is that we can use data from one modality, let's say the sequencing data, as training data for a model that, let's say, operates only in images. So the goal here would be, for instance, to train a model that predicts from one of these H&E stained pathology images what molecular profile this patient has. And we work on both of these areas. One specific additional advantage we have is that we have longitudinal data. So we actually know the progression and the survival of the patients. So ideally, going back to this specific case of prostate cancer Gleason grading and the label messiness, we would like to not train machine learning models on the noisy, subjective human labels, but we should really train it on the biological ground truth of the patient survival and the progression. And that is exactly where you need longitudinal data in addition to multimodal data. And this is one of the core strengths that we have at Tempus. We have access to this data, we generate it with our clinical partners. And based on that, we can train models to predict survival directly. And the goal of this is obviously then to determine the right therapy or the right treatment for a patient. So we have some really interesting work going on in this space, and please stay tuned for more updates and some publications that we're working on. Another related application that we have talked about more publicly already about is that we can try to understand a bit better what is actually in these pathology slides and really go down to the level where we can link it to molecular data. So here, for instance, an image of, again, an H&E stained pathology slide, where we have classified what types of cells are we actually seeing, which are the immune cells, which are the normal epithelial cells, where's the tumor, where's the stroma, so all the different histologies. And this is extremely important for immunotherapy. So classifying, let's say, which of these cells are tumor cells and which of these are immune cells gives us the ability to determine what kind of immune infiltration scenario we are facing. For instance, here on the left side, we see what's called an immune desert. So there's pretty much no immune cells around the tumor. In the middle panel, we see an immune exclusion, where the immune cells are outside of the tumor but have not infiltrated it. And on the right side, we see an immune infiltration, where immune cells are actually invading the tumor. And these three different scenarios give rise to very different immunotherapy responses. So we can use that to predict response and also alter the treatment. And this is just one example of the advantage of multimodal longitudinal data that we have at Tempus to go beyond diagnosis and identify what is the right treatment for every patient, and with that, make the idea of precision medicine become a reality. And with that, I'd like to close and thank many of my former and current colleagues, some of them are listed here, and many others, and thank you for your attention.